My name is Sean Bentley. I've been with GoEngineer and SOLIDWORKS in general for about 12, 13 years now. And I've specialized in the simulation side of things. I've got a lot to share with you today, and time's pretty short, so let's jump right in. So on the agenda, first we're going to start off by introducing you to the different simulation packages, kind of like what I did if anybody attended the structural session, but this one will be more focused on the thermal side. Then we'll talk a little bit about a few heat transfer fundamentals, stuff that you're likely already familiar with, conduction, convection, radiation, but we're going to talk about how this applies to our different thermal analyses studies that you can set up with SOLIDWORKS. And then we're going to go through a specific example. So it's going to be a microchip. In this case will be our thermal study, transferring heat to a heat sink across a PCB, put a fan in there. But I'm going to show you three different versions of running this study. First of all, I'll see what kind of answers we can get with just a pure hand calculation, which I'm going to use a Microsoft Excel spreadsheet to do. I'll go through very briefly what the rough ideas are there, but then we're going to compare these assumptions to if we run a SOLIDWORKS thermal study versus a flow simulation study and see how the results stack up. Starting though with the SOLIDWORKS analysis types. Many of you might already be familiar with this this checklist here. I guess the simulation standard comes with static analysis for assemblies and time-based motion. Simulation professional, though, is where you start to get access to some of the thermal analysis capabilities. And this is one of the key things we're going to talk about today. Then on the side we have SOLIDWORKS flow simulation. Now this is a package that's sold separately from these packages. Simulation Pro doesn't include the SOLIDWORKS flow simulation, but this tool here as well is capable of thermal analysis. So really we're going to focus this presentation down on this little subset here, specifically the thermal analysis available with SimPro versus the SOLIDWORKS flow simulation, and see how those results stack up. So next part here I'd like to cover is some heat transfer fundamentals. Talk a little bit about how these apply to the thermal analysis and flow simulation. Now, so the modes of heat transfer, there's three modes through which heat transfers from one body to another. It's either through conduction or by convection, if we're talking about heat transfer from a body to fluids, or also thermal radiation. How are these three modes accounted for within thermal analysis, flow simulation? That's sort of the question I want to try to dive into. So talking about conduction first. So conduction is the heat transfer through solid bodies and from one solid directly to another. We'll talk about that in a moment. So here's the example we're looking at is this chip transferring heat to the PCB, and you can see the temperature rising on the components, and heat would need to be transferring across the PCB media and also through these other bodies to get to the heat sink. So one of the main bodies we're going to look at quite a bit in this webinar is going to be how do we model the PCB. Okay, that'll be a couple slides on that. So how do we do this inside of a thermal analysis that's part of SOLIDWORKS Simulation Professional? Well, if you're going to model the PCB or any other material, you just simply do it by applying conductivities. Now in the case of a PCB, it's going to have an orthotropic conductivity. So we'll have to model in a conductivity in the X direction, a different one in the Y, this is going through the plane of the board, and then maybe a similar one in the Z. We'll have to approximate that entire PCB body perhaps as a orthotropic material. That's one way to model it. Now in flow simulation though, we have a similar method, okay, but it's a little more sophisticated where you can plug in layer thicknesses and percentage of cover of the conducting material, and you can specify the conductor material conductivity. In this case it'd be copper, about 401, and then what's the material conductivity of the dielectric, and it'll come up with these same coefficients for you. You won't have to manually try to hand calculate them out to come up with some average coefficients. Flow simulation is going to come up with those same numbers for you, and you see here I've kind of mimicked it, 53.19 for the in-plane conductivity. You see that for the X and Z, and then 0.34 for the normal conductivity. You see I've mimicked that there. So flow simulation does some of the work for you, though it ultimately gives you the same material, and it should produce the same results if I were just running a calculation on the PCB by itself. Okay? And we're going to see this kind of trend with the differences between thermal and flow is it's sort of like thermal analysis can do it. It just takes a little more user input to get it to do it. Now another aspect of conduction is transferring heat from body to body. Okay, so in this case, if we want to model things like thermal grease, if we're going to transfer heat from the CPU chip to the heat pipe that I have modeled here, it's not a perfect heat transfer across there. These two components are put into contact, and we might put some thermal grease on there to try to improve that contact to make sure that we get pretty good heat transfer across those bodies. Now the way you do this in thermal analysis is through contact resistances. We'll set up a contact resistor, plug those in, and key in either a distributed or total contact a thermal resistance for that contact. Now compare this to flow simulation. We have the same kind of contact resistances, but with a few extra options. We can specify material and thickness rather than just keying in the resistance or resistance integral like you see here. But also we have an option for thermal joints, where we can just do direct contact between two faces that are separated by some distance. They don't even have to be touching or near each other. Two resistor components, where we can key in thermal resistances on a heat generating component. We're going to see more of this in a moment with the CPU chip. And also heat pipes, the heat pipe option as well just allows you to tell that heat pipe it's going to transfer heat from one body to another with a thermal resistance. Okay, so again, you can sort of mimic all of these features over here that flow has with this contact set, but it just takes a little more work to set that all up. This gives you more the flow simulation gives you more versatility with how it handles conduction. So overall, the difference between thermal analysis and flow simulation as far as conduction modeling goes, they both have about the same type of capability, but flow simulation just makes it easier a lot of times to model conduction. Now the real big differences we're going to see in actual functionality is on convection. This is where we'll see that flow simulation does a lot better job of modeling convection than what we might be able to do inside of thermal studies. So convection, of course, is the heat transfer from solid to fluid media. Okay, so if you have the heat sink is a great example of where we're going to see convection, and here I've got our heat sink modeled inside of a thermal study, where I've got a convection where I just plug in a number, one number that describes the convection environment. So the thermal analysis, it's not actually calculating the airflow around the heat sink so much as we're just entering in a number, one single number that describes the general airflow environment around that. So if you key in a big number for the convection coefficient, it's kind of like you're simulating, oh, there's a lot of air flowing around, it's got very good airflow. If you key in a very low number for this convection coefficient, then you're assuming that the airflow is very poor, and maybe it's just free convection, doesn't have any fan blowing over it. So you're controlling that convection with basically a single number, whereas in flow simulation, we are modeling the convection. We actually do simulate the air flowing through the domain through the use of fans and openings in your model. Here's a fan that's sucking heat out. This will be kind of what we'll show you in a bit. We'll set up a study and kind of walk through this. But here I've got this outlet fan. And then based on that, it calculates the convection coefficients, which are going to be, in this case, very non-uniform. You see there are some regions where the convection coefficient might be 50 if I have that fan blowing fast enough. But there's also other regions where the convection coefficient looks like it's down in 25 or even down close to 0 on some parts of this heat sink, rather than just assuming the whole thing is 50. Okay. So that's really, on the convection side, that's really where flow simulation shines the most. Okay. Now, there is another mode of heat transfer as well, radiation. And so radiation is the heat transfer through electromagnetic waves, and the different tools we're going to use, thermal analysis versus flow simulation, we'll model this as with some ray tracing capability for the most part. So in the case of thermal analysis, how do we model radiation? Well, we do it by simply selecting the faces that are going to emit radiation and keying in an emissivity for those faces. Now it can do some transfer from face to face. If you have other faces that also have radiative surfaces, you can actually see the heat transferring from one face to another. It won't show you the rays per se, but you will see that the temperatures and the heat flow will illustrate the heat transfer from surface to surface. But it's just through, again, selecting faces and specifying emissivity for those faces. And the emissivity just describes how well it radiates. If you key in a low emissivity, it has no radiation, and emissivity of 1 is its maximum value for radiation. Things like asphalt or black tar would have a very high emissivity because they're going to emit as well as absorb all the incoming radiation. Now on the flow simulation side, we have the same kind of functionality where you're able to specify emissivity on all the faces, but with the advanced radiation module, it's part of flow simulation, you can do some more sophisticated things with it. We can even specify wavelength dependent radiation, where here's the daylight spectrum. This is the radiation coming from the sun. Most of it is in this wavelength here, which is like visible light, but there's also infrared on this end, some infrared, which is causing heat, and also ultraviolet on the low end of the wavelength spectrum. You can also specify the same type of thing on your solids as well. If you have like if you're thinking of automotive glass as a great example, how it absorbs a lot of the incoming ultraviolet radiation but allows visible light to pass through, we can model that inside of using the HVAC advanced radiation module inside of flow simulation. And so the basic idea is if you have some sort of radiation maybe coming from the sun or some source, some of those wavelengths will get absorbed, blocked, some of them will be allowed to pass through, and we'll see the effective thermal analysis from that, the heat transfer from those radiations. So you can do some of the similar things here you can do in flow, and more. Okay, so those are the three modes of heat transfer and how the thermal analysis versus SOLIDWORKS flow simulation handle those. Next, what I'd like to get into is we're going to do this a hand calculation, and then we'll do a thermal analysis and then the flow study and show you what those look like. So in order to walk through the hand calculation, though, in order to walk you through this first part, I kind of have to introduce you to a few basic thermal analysis principles that this hand calculation is going to follow, and also these other studies will follow as well, so that we can make some good comparisons between them. So since circuits can be complicated, and we have many, in this case, this board might have many heat generating components, a lot of resistors which might generate heat. We're going to start pretty simple though. Okay, our board's just going to have one heat generating component so that we can we'll be able to do this comparison more easily. Now, granted, as soon as we add the other components, that's going to make the hand calculation very difficult to do and do a comparison. But let's start with a simple one, compare those, and then you can scale things up later. Now, the basic principles behind some of the calculations we're doing inside of any thermal analysis tool, we're going to talk about this concept called thermal resistance in a bit more detail. I've kind of alluded to it a little earlier on in this presentation when we're talking about, I used thermal grease as one example, but thermal resistance can apply across the board to a lot of components in your model, as well as the thermal resistance to the air. So it's important that we just talk about this briefly to really clarify what we mean by thermal resistance. Now, a very common analogy that's used is to compare it to electrical circuits. In looking at electrical resistance, if you've done any kind of circuits class or anything like that, you might know V equals IR, which is very similar to on the thermal end of things, T equals Q theta, theta being the resistance. The basic idea, though, behind this equation is that if you have a lot of heat that you need to get rid of, that's Q here. If you have a lot of heat that you need to dissipate, and there's a large resistance to dissipating it, you can't get rid of the heat, well, your temperatures are going to go up. That's basically all this equation is describing. So if we look at this example here, we have an LED which generates heat, and the manufacturer will provide us with some thermal resistance numbers based on their testing. They'll give us, because it's too complicated to model the junction to the case, they'll do testing on that, and the manufacturer will provide you with that information, the junction to case thermal resistance. But then some of these we'll need to model ourselves, either through by running thermal studies or flow studies. We'll need to come up with the substrate materials thermal resistance. This one might be provided by the manufacturer. And then the heat sink to the ambient thermal resistance, that's done by a flow study. We can figure out this thermal resistance here by running a fluid dynamics study and running air over this heat sink. So we can kind of fill in the blanks. Now here, looking at our junction temperature, which is at the very top here, junction, all the way down to the ambient temperature. There's a big resistance that can go between those, and if we just do a quick if I just do a quick hand calculation here to show you the basic principle, if that LED is generating 3 watts, that 3 watts has to get to the ambient temperature, 20 degrees C, and if the entire thermal resistance of our circuit is 20 Celsius degrees per watt, well, the math is easy. We take your 3 watts, multiply by the 20 Celsius degrees per watt, and that's going to equal an extra 60 degrees C that this thing has to heat up to. In other words, it's got to be 80 C in this thermal circuit. Okay. Now actually, thermal circuits are quite a bit more complicated than just one resistor, or just being a series of resistors. This one looks a little more like the one I'm about to show you in our hand calculation. Okay. So let me go ahead and pull that up now and show you the rough idea. So here I've modeled the chip. The chip generates 12 watts. Okay, it's in the top here, and then the path that follows to get to the ambient temperature, or to the ambient. And if I just take a look at one of these animations, the chip, it has to transfer heat through the heat pipe to the heat sink and then to the air. Okay, but it also has to transfer heat from the chip down to the board, across the board, and then to the air. It's got these couple of pathways it can take to get to the air. So that's what this hand calculation models is. This here we have this chip that's generating 12 watts, and it has to go through the junction to case thermal resistance to get to the case, then from the case to the heat pipe, then from the heat pipe to the heat sink, and then eventually to the air. And if I increase the resistance anywhere along this path, we can see this temperature, the junction temperature that I've hand calculated to be 7961. If I, for example, say that the case to the heat pipe has a bad thermal interface, if I, in other words, increase this resistance by a lot, you see my temperatures, my junction temperature goes up by a lot. And the effective heat that's traveling down this pathway has been reduced substantially. Now I got pretty much all 12 of these watts are taking this pathway here, and I've got these little bars on the side so you can see very low heat versus high heat. Let me go and bump that number back down, make it more realistic, and now I get a more even distribution of the heat going to the left versus to the right. Now some of the key assumptions I had to make if I'm running a hand calculation like this, though, like how did I model the board? Well, I did it similar to the way flow simulation does. I created a conductivity table, but I have to make some assumptions about how the heat transfers through the board. Let me show you. So I had to make an assumption that maybe the heat goes this way first and then goes this way along the length of the board. So I have to take into account the conductivity through the board first and then across the board second. So I had to put those in series, but I'm going to say that on average maybe it has to go halfway through the board before it has to go across the board. So I did these averages, and that's what I've plugged into this equation here to come up with an overall thermal resistance of the board. Okay. And also similar for the heat transfer of the air, I just had to make some assumptions about the convection coefficients. Here's where my assumptions are in orange. I just assume maybe the convection coefficient based on this table here that you can find online. For forced convection, low or moderate speed, it's going to be between 10 and 100. I'd assume maybe it was 20, 10, and 10 for these heatsink, case to air and board to air parts of the circuit. And then I come up with respective thermal resistances for those. So you see all the assumptions that go in line with trying to do a hand calculation like this. So let me kind of paraphrase that or summarize. So ultimately, the assumptions I had to make to do the hand calculation, heat transfer through and across the board is a series resistance. Kind of talked about that a moment ago. I'd assume that the bodies themselves, like the copper body, didn't have had perfect heat transfer across it. It was able to distribute the heat across it perfectly without any resistance. I had to assume some convection coefficients. Okay. I had to assume the air temperature was distributed uniformly throughout the entire domain, and I also just had to make an assumption about the fan just being at maximum output, so it was able to transfer heat to the outer environment as efficient as possible. And I ultimately arrived at a temperature that was 59.6 degrees above ambient. That's the 79 that I saw in the spreadsheet. So an extra 59.6 above the 20 degrees Celsius ambient. Now let's compare that. Let me run a thermal study next. See what kind of results we get out of that. So here I'm in SOLIDWORKS here, and I'm going to set up a brand new thermal study. And using SOLIDWORKS Simulation, I'll go ahead and apply materials to my parts, assign the contacts between them, also assign the loads. So let me start at the top here and apply the materials to the different components. Now in this case, I've got my heat chip modeled as two bodies, one for the junction and one for the case. I'll just use a high conductivity body for those though, since I'm not actually modeling the chip perfectly accurately. I'm just going to be modeling it with thermal resistances in a moment. I'm just going to go ahead and use a high conductivity material for those two. I'll just use copper or something. Now the heatsink is made out of copper, so that one I will also use that copper conductivity for that as well. For the board, the thermal resistance of the board is really important for me to model to get that accurate, because that's how heat transfers across this board. And I've done that by using that hand calculation tool built within Flow Simulation or in my spreadsheet. I've come up with an orthotropic material that has these conductivities across there. I'll go ahead and assign the directions if I just use the front plane in my model. But if I use the front plane, that'll use the default coordinates that we have down here. Okay, so you can see the low conductivity direction is in the Y through the board is low conductivity, and along the plane of the board is the high conductivity. Okay. So there's my board, and then the rest of this heat pipe. I'm going to model the heat pipe as, you know, there's no a heat pipe geometry. It has higher conductivity even than copper. The way I'm going to model it is I'm going to use just a very high conductivity material for it, but in order to actually get it to be accurate, I'll be using I'm going to use this material that has virtually no resistance. But in order to get it to be accurate, I'm going to model it as with a contact resistance. I'm going to say that this heat pipe effectively is making the thermal resistance between here to there be about 0.3 Celsius per watt. And then finally, I've got these couple extra components here. I'll just assign a typical connector material. Has a conductivity about 20. Okay, so about 1/20th of copper as far as the conductivities of those go. Okay. So once I've got my materials assigned, now let me go ahead and take care of defining my thermal load. This will be a heat power prescribed to the chip body. Okay, specifically I'll say this will be like where the junction of my chip is located, and bump it up to 12 watts. Now that 12 watts needs to go somewhere. It's 12 joules of energy entering the system per second. It needs to go somewhere. I want it to go up through this pathway to the heatsink, but also want it to go down into the board. Now it's going to bump into resistances along the way though. And this is where I need to model in those thermal resistances, okay, those contact resistances in this case. So if I go ahead and explode this view, pulls these components apart, makes it a little easier to assign my contact resistances. I'll do that through the use of some contact sets. One thermal resistance I'll model is from the chip to the case, to the outer case. Okay. So I'll go ahead and select the internal faces here. I've got a little square face inside of there, but that's between these two separated bodies. Okay. And this resistance is going to be 0.28. Okay. This came from a manufacturer for this chip. They gave me a junction to case thermal resistance of 0.28. Now I'm going to use a thermal paste here to connect this thing to the heat pipe. Okay, and that thermal heat pipe, that thermal grease, on the packaging it advertised a thermal resistance of 0.0007, somewhere in that ballpark, between these couple of faces. So I'll go ahead and plug in that value for that thermal resistance, 0.000742. So that restricts the heat flow up through this pathway a bit. And also, since I modeled this as a zero resistance component, it actually does have a bit of resistance as it transfers across here. But I'll model that with just another contact resistance on the downstream end, where I'll just apply a connection or a contact between these couple of faces of 0.3. Okay, and that's based on the thermal resistance of the heat pipe in general. Alright, so that models this pathway, but then how does the heat get lost from this heat sink? It has to transfer to the air. And so at this point, in order to transfer that heat to the air, let me go ahead and collapse this for a moment. I need to model this in as convection. So I'm going to go ahead and define a convection onto this body. Now, the way I can do that is if I can select all these faces, every one of them individually. It could be pretty tedious. Or instead, I've already created a selection set. And part of this heatsink component, I went into the heatsink component itself, and I created a new study and used this select all exposed faces to create this selection set, which grabs all the faces of that heatsink. You can kind of see it's kind of neat showing when I show the graphic symbols, it shows them selecting all the faces one by one. Okay, let me turn off those graphic symbols for now. I'll key in a convection coefficient though. I'm going to assume maybe 20. There's an external fan that's pulling air out. I'm assuming that maybe the convection isn't perfect, and then I'll key in a ambient temperature 296.58. That's about 23 degrees Celsius. So I'm assuming the internal air inside of here is about 3 degrees warmer than the air on the outside of our computer box. Okay, so that's the convection on the heatsink. That's the main thermal pathway. But I also want to define the thermal pathway through down to the board and across the board, and also the convection on the board itself. So I'll do one more convection coefficient, where I'm going to select all exposed faces. Now this is going to grab too much. It's going to grab the heatsink as well, which is too much. But all I'll do here is if I just click on that selection set again, it'll turn off all the heatsink faces, and I'll be able to apply a different convection coefficient to all of these ones. I'll key in a slightly smaller one, about 10 instead of 20. Okay, so you can kind of see the assumptions I'm having to make. I'm going to turn these faces off too because they're going to get pretty low convection. So the assumption I have to make here in the thermal study is that we just have this one number that describes how heat's transferring to the air. Okay, and also same thing, 296.58, assuming that internal air is at 3 degrees warmer. All right, and this study is pretty much ready to go. Oh, I did forget one more thing. I'm going to go ahead and explode the view one more time. Okay, I forgot to put in that heat transfer from here to here, from our CPU chip down to the board. That's another thing provided by manufacturers, is they call it the junction to board thermal resistance. So for that one, I'll do one more contact set, and they provided me with a number of 3.13 for the junction to board thermal resistance. Alright, so with that, I'm now ready to run this simulation. So let me go ahead and kick it off. Just go ahead and hit calculate. Now I would do some mesh refinement to it as well to kind of clean things up, but we'll just run it as is to get a quick and dirty result. Alright, so I've run this study. I get a temperature result. I can probe. Take a look at my peak temperature. Okay, 73 on the case, 75 on the CPU. So you can see that 75 here, and then that's where my heat is being generated, 12 watts, but it has to transfer through the case to here and through here. Okay, so we're losing temperature all the way along. Okay, and you can see the big thermal resistance I keyed in that 3.13. You can see the big temperature drop from here down to here. It's 54 up to 75. Okay. So to summarize this thermal circuit that I've just modeled, here's what, if I compare it to the hand calculation I did, here's the thermal analysis I've just run. And if I put those numbers into this table, kind of fill out the table a little bit, so you can kind of see where I'm plugging this in. Now some of these came from the hand calculation. Some of these numbers, I pulled this number in right from my hand calculation, so that hand calculation was helpful for me to run my thermal study. And you can see one comparison is my assumed thermal resistance on the board. When I did the hand calculation, I got 5.65. But when I ran the thermal study, it came up with a different number, 4.18. This should be a more accurate thermal resistance, okay? Because we actually modeled that board in a slightly higher degree of detail than what we did with this assumed thermal resistance I did over here with just the series circuit. Okay. Now ultimately the difference is about 4 degrees. Let me go back to our PowerPoint. So here we see our thermal analysis came up with a close answer to my hand calculation. It sounded like it was pretty good. But we still had to make it should be better, but we still had to make a few assumptions. We had to assume the convection coefficient still. We had to assume the air temperature is distributed uniformly. We're not really accounting for the airflow around this board. Okay, we're just using convection coefficient to describe it. And I'm also still assuming the max fan output, which is giving me that 23 point whatever degrees Celsius inside the chamber instead of the outside ambient of 20. So next what I'd like to do is let's show you the same study set up inside of SOLIDWORKS Flow Simulation. So finally, let's run this one more time. This time I'm going to move over to SOLIDWORKS Flow Simulation with this thing. Okay. Now I've modeled this thing a little different for a flow study. For example, let me go to this flow configuration I've set up here, because I can include a bit more detail than what I can get away with on the thermal study. For example, here I've included some of the vents, the air vents. Okay, see I've cut out some holes here and here, and a place where I can put a fan right in front of that heatsink. Okay. So using SOLIDWORKS Flow Simulation, which is just another add-in similar to the SOLIDWORKS Simulation, you turn on SOLIDWORKS Flow Simulation, and with this add-in, we can set up a new study. A lot of times I'll use this wizard as a starting point for my new study. Ooh, looks like I might have to boot that back up again. By the way, this model I'm using, it's actually one of the Flow Simulation tutorial models, but I've taken some components out just to keep it a little cleaner for a presentation like this. But it is it's the very last. It's one of the very last Flow Simulation tutorials. If you go, and if you'd like to see this tutorial, just let me know. I can maybe send over the document to you. But it's under the electronics cooling examples here. Okay. So here it's a more sophisticated looking model, right? But they simplify it down a bit too, and they have a couple chips that they're modeling in there. But we're just keeping it simple with one for now. Alright, so back on track here. So what I'm going to do is we're going to set up a new flow study on this. Usually I'll start with the wizard. And the wizard's going to walk me through the steps of creating, what kind of fluid am I going to be using? Am I going to use air, water, that kind of thing? What kind of physics I'm going to take into account in this study? So it's going to set up a lot of the background details. I'll go ahead and next through most of the steps here because I just want to get to really the critical things I want to show you on the thermal side. Okay, change my temperatures to Celsius. Important, I'll turn on heat conduction in solids. You can just run flow studies where you're just having air flowing around bodies and calculate drag coefficients. But in this case, we're interested in the heat transfer. I'm going to leave radiation off for this first study since I didn't take into account the thermal study. Also, I'll turn on gravity so I get some buoyancy effects. And I'll have it pointed in the negative y direction there. Then we'll use air, of course, for our fluid. For our default solid, let's use metals. I'm going to use, or pardon me, going to my alloys. I'm going to use stainless steel 321. That's just going to define the solid it's going to use. If I forget to assign a material to something, it's going to assume it's made out of stainless steel 321. But that's also going to be the material I'm going to use for the enclosure, the surrounding enclosure. Now also, since I'm running this as an internal study, I'm not going to account for all the air outside of the domain. I'm just going to calculate the air that's inside, okay, to save me some calculation time. But I do want to account for the heat transfer that's going through the wall to the outside air, and here I will key in a convection coefficient just to simplify the heat transfer to the outside air since I'm not modeling it directly. And finally, the rest of this stuff, we'll leave the initial conditions as default, and then we'll get to the good stuff. Okay, so here, to set up a study inside a flow simulation, I can walk through some of those same kind of steps, but you see here I have options for fans and 2 resistor components, heat pipes, printed circuit boards, things that aren't available in the SOLIDWORKS Sim Pro thermal analysis tool. Okay, more fine-tuned components basically. So I'll go ahead and assign the material though, similar to what I did before. For example, the heatsink body, that'll be made out of our copper material. The board, I'll use this printed circuit board tool to describe what that board's made out of. And I've got this PCB material that I've created. You can see this, if I go to this Tables and Curves tab here, you see the layer thicknesses with the percentage cover like I showed you in a slide earlier on. If I go to Item Properties, it's going to come up with these coefficients based on what I key into that table and what I key in up here for these numbers. So I've already tuned this. I've already got this board material ready to go. And it automatically knows the directions of the board based on just the size and scale of the board. It's expecting a big rectangular prism, so it's using the smallest dimension of it as the through thickness direction. So it really simplifies creating that board material. What else? Oh yes, and also I'm going to insert another material for our connectors. Okay, and since this is flow simulation, the electronics cooling module, we actually have some IC package materials built right into the interface. And I'll go ahead and use these for these couple of connectors. So no need to manually create my own materials here for the most part. Okay. Now next what I'd like to do, let's go ahead and assign, I'm going to set this up in the same kind of order we did that thermal study. I'm going to start with the heatsink or pardon me, I'm going to start with the heat generating component, and then we'll model the thermal pathways. So this guy generates a lot of the heat, the chip. So I'm going to use the 2 resistor component tool, which is also part of the electronics cooling module, to define this as our heat generating component. And I'll define this side, the top side. This is going to be the case side, so it knows which way is the board, which way is the case. And I'll select from our electronic cooling module database the material PBG-AFC 35 by 35. Okay, and if I take a quick look at this, you'll see all it is just a couple of thermal resistances, the same ones that I keyed into that thermal study a bit ago. 0.28 going to the case, 3.13 going down to the board. I'll key in 12 watts for the overall heat generation rate. Okay, so that tells it it's got a pretty big thermal resistance going down to the board, and the board itself is a pretty big resistor as well, so probably more heat's going to go up, I'm hoping, through this channel. But we also have a thermal interface material we need to put on here. That's going to be through a contact resistance. Okay. Some thermal paste is going to be right on the bottom face of this this heat pipe here. I'm going to use the select other command to grab that underside face of it. You can kind of see it's highlighted there now. Okay. And we'll select from our database of interface materials this bond ply 660 at 10 psi. Okay, it's just another, and it's just exactly what I keyed into that thermal study. So that, remember, that thermal study could do all this. The thermal study in SOLIDWORKS Sim Pro, it could do this, but I said I didn't have a database of materials I could pick for these types of things. You had to plug in the numbers. Whereas here I can kind of browse through the database. Okay, so I'm going to go ahead and assign that thermal grease to that. Okay, then the heat pipe itself. I'm going to insert a heat pipe, and I'll say this component is the heat pipe, and it has an internal resistance of 0.3 okay, Kelvin per watt. And I just have to tell it which face it enters and which face it leaves out of the heat pipe, so it knows what faces to put this thermal resistance onto ultimately. Okay, so I'll specify, I'll use that select other command again to be able to select this face inside here. Okay, that's in purple now, and it's going to leave out of this face I have over here, and I've split the faces up a little bit so you can kind of see. Okay, looks like it's going to be that one there. Okay, so that tells it this pathway to the heatsink. Now the heatsink, it's going to transfer through the heatsink into the air, so we need to model the air a little bit here. For example, there needs to be a fan on this face, so I'll go and insert a fan, place it onto this face here, and this is going to be an outlet fan for this test. I want to see what happens if I put an outlet fan sucking air out of this, and I'll select from my again my electronics cooling module database, my PAPS 414. That's the one I plan on using here. Okay, and this has a max flow rate. This fan has a maximum flow rate of 0.0028 cubic meters per second. That's what I assumed in the hand calculation. That flow rate's also what I assumed on my Sim Pro thermal study as well. Now in actuality, because there's some holes here and there's some resistance to flow, it actually probably will get a less flow rate than that. Okay, we'll probably maybe be along here in this part of the curve perhaps. Okay, so we'll see when I put in some of these resistances to flows what happens to that fan. Okay, and I'll model those resistances with some perforated plates. For example, here, this is not just purely open here, otherwise you stick your finger in, you cut your finger on the fan, there's going to be a plate with holes in it right here. That's going to restrict the flow a bit. And I've already modeled that as a round holes plate, okay, which is just you key in a free area ratio. It's half open, half closed. That's basically what we're saying here. So those holes keep it half open. That's going to cause that fan not to blow quite as quickly perhaps. And also the air flows in through these ports, so I'm going to put perforated plates there and there. Okay, I'll assign a environment pressure boundary condition to say that it's open to air here and it's open to the air there. The air is going to flow in through these two ports, and a similar perforated plate on those two openings, okay, to kind of restrict the flow. It's not wide open. It's got a perforated plate to restrict it a bit. Okay. So that pretty much does it. I don't need to put any more contact resistance. A lot of the thermal resistance was modeled with that 2 resistor component. So the thermal resistance down to the board and up to here, at least up to the case. And the rest of this is already, I think we're pretty much ready to go here. There's a lot of stuff I assigned, so just kind of doing a quick once over to see if I forgot anything. But all right, so let's give this a run. So I'll tell it to mesh and solve it. We'll see the solver window opens up. Okay. And oh yeah, there is one thing I did want to include, and something that something's really handy for the solve process too. Let me turn this off for a second here. Okay. When I set up this 2 resistor component, I wanted to also tell it to include temperature goals for the junction, case, and board. So I want to know what the temperature of the junction is, what the junction of the case, what the temperature of the case is, what the temperature of the board is, and I can fill out my spreadsheet with that data. So by including those goals, I'll be able to monitor those things while it's running my simulation. Since I already meshed it, it doesn't need to remesh. Now it just jumps right to the calculation. Okay, and let me go ahead and plot those goals. Let's look at all 3 of them. So here you see the junction goal, of course, is the highest. That's where the temperature is the highest, where we get the 12 watts of heat starting from. And then to the case, it drops to 71, and if we're going down to the board, it drops to 56. That kind of tells me that there's probably not a lot of heat going down to that. Not as much heat going down to the board as what's maybe going up to the case, or actually we had a much lower thermal resistance to the case. That's probably what's really going on there. Okay, but you see these couple of temperature drops. It's already done running. It looks like these values converged, they stabilized. And now I can take a look at some of the results. Now I did run this with a pretty coarse mesh just now. I did a few where I did a much finer mesh, and those are the results I'm actually going to present to you. My mesh is a little coarse for this study. But let's take a look first of all. Let's jump right to this flux plot here. It's a really handy tool for thermal analyses. And what I'll do is I'm going to tell it to use all components, and you can see it's almost like that hand calc I showed you. Let me organize this a little better. I know it comes up a little disorderly. Let me put the PCB over here. Let's put the I'm going to filter out some of there's some low heat transfer bodies in here. I'm going to filter those out. Say get rid of those. Anything less than 0.1 I don't care about. Let's take a look at the transfer to the heat sink, the heat pipe to the heat sink over here, and then down to the air here. Nice in order. What's this guy? Oh, that's one of those extra components, and that's 0.12. I'll filter that one out too, actually. Okay. So here's the overall thermal pathway. You can see the heat enters into the junction of the chip. Then it goes to the left and to the right. Actually, equal amounts, looks like. So looks like a lot of it goes left, about half of it goes left, to the heat pipe, to the heat sink, ultimately to the air. And then the other half goes to the right, to the PCB. Okay, then to the air. You can look at those thermal pathways and try to optimize your model around these. You can see that a lot of it went to the, I guess we could maybe increase if we decrease the thermal resistance of that grease that we used, maybe we can get more heat going this way and lower this temperature in the top here. This is kind of a nice graphic. You don't get this out of the SimPro thermal analysis. It shows you those heat pathways. You sort of have to manually probe your model to try to get something like this out of there. But also importantly, in a flow study, we can look at things like flow trajectories and see the air flowing through here. So let's just do this as little balls or something, or arrows, I guess, are fine. Okay, and let's look at temperature, or velocity rather. Okay, so I can see air flowing, how it flows around this domain. We see some recirculating going on back here, not much going on back there, but okay, so we're actually modeling that air, and with the air modeled in here, we can see things like convection coefficients. Let's look at the convection coefficient on this body, because we assumed 20. That was the assumption in our hand calculation. How good was that assumption? So let's look at a heat transfer coefficient on this body. Okay, bump this down to maybe 50 or something. And you see my assumption probably wasn't too far off. Okay, looking at the numbers here, 0 to 50. It seems like the average is in the ballpark of the green area, about 20. And I can look at that average if I look at a surface parameter on that same body. I can probe that entire body for its heat transfer coefficient and ask, What's the average? It's about 16 actually. It was actually a little lower than my hand calculation. But my hand calculation wasn't too far off. My guess wasn't too far off. Okay, we can grab all the bodies, look at the overall heat transfer coefficient through the whole domain. But also importantly, looking at the temperatures on all the bodies as well. Okay, so let's look at temperature of the solids on all the main bodies here. Include those couple of connectors. I won't include the outer shell. Okay. All right, it looks similar to what we saw in the thermal analysis, but let's compare. Let's actually look at the numbers. Okay, so back to our PowerPoint for some wrap up here. So here were the numbers. When I ran the flow study, I actually got a little bit lower of a temperature. Okay, it was about, now the coarse mesh I ran, I think it would have been plus 71 or 51 or something, or so I got 50.6 when I refined the mesh. So you can see they're all pretty close for this simple problem, but as the problem gets more complex, as it gets more convection dominant, if the convection is really important to get it accurate, that's where we're going to start seeing maybe some big differences between these results. Okay, but for this pretty simple model, I was able to get them to line up pretty close. Now, by the way, I neglected radiation through all these studies. If you're just curious, if I included radiation, that does drop the temperature a little bit, about 3 degrees. That junction temperature drops by about 3 degrees. Okay. So, like I showed you, we showed you this thermal circuit here, and if I include radiation, you can actually kind of see the radiation leaving from the different components, and with proportions of those. A lot leaves right from the chip because it's at a very high temperature. But also the heat sink loses some, and the PCB being a big surface area loses some through radiation too. That really helps. It lowers the overall resistance, the overall thermal resistance of this system. Okay. So to wrap up, what we covered in this presentation, we talked about the tools, Simulation Professional, which has the thermal analysis, and also SOLIDWORKS Flow Simulation, a separate tool for running flow studies, and we compared them. I walked through some basic principles behind some of the differences you'll see: conduction, convection, radiation, and also thermal circuit modeling. Some of these principles were covered in this presentation, and then we actually did the comparison between a hand calc thermal study and a full-blown flow simulation study. Further training, if you'd like to learn more about these topics, if you've already owned a seat of thermal analysis or flow simulation and you'd like to get more training on it, we offer, there's a 4-day bundle. Okay, 3 days that goes over simulation fundamentals. Okay, talks about things like meshing and what's a good mesh, that kind of thing. And then the additional 1-day extension covers the thermal analysis specifically. There's a couple lessons on it. But once you know a lot about running just structural studies, running the thermal studies becomes a no-brainer. Then separate from that, though, is if you go down the flow simulation route, the SOLIDWORKS flow simulation route for your thermal analysis needs, then we have a 2-day class that talks about the SOLIDWORKS flow simulation, focused on flow studies. And then a separate half-day electronic cooling module, and another half-day on the advanced radiation side of things, too, if you'd like to go into more detail on those 2 topics. So with that, thank you for attending this webinar, and thank you all for listening.